You have stuff for me. 3 sections worth of stuff. Wow.
Exactly. My calculator is broken up. We have the same settings, but like.
Okay, that's in parametric.
Yeah.
That's the right picture.
That's the right picture.
Yep.
Because when I use the other calculator, like the old fashioned one, there's something different.
That sure looked like the right picture to me. We've done a lot of stuff. So today is, what do you want to know? About the final exam, about material, about review sheet, about anything for this course. What questions do you have? Yes. The version that I have drafted at the moment is (18). Again, some of those have multiple parts. So I would say it's not more than about 20, 22-ish questions altogether. But I haven't finished the draft. Other questions? I would say it's a little more diffuse, but it's like a third from the material for exam 1, a third from the material for exam 2, and a third from this most recent material. The goal is to not pull crap out of left field you've never seen before. If I think it's important, either I've already tested you on it, I've given it as a homework question, or I've talked about it a lot as an in-class example, there's nothing there's nothing that's going to be like, I've never seen this before. But that's my opinion. Yours different. Other questions? Yes?
The last exam, for the formula, it was like solving for, you get 3 angles with 3 sides.
Right, our solving a triangle.
Right. So one of the questions, I think, second page, didn't have that one part.
So
completely missed the
these are the
next
two,
one.
these are the two solving, oh, no, that was this one.
Right, so there's
Okay.
like a follow-up question.
Yes,
Therefore,
however, I would point out to you something important. If you screw up part A, but you use the numbers you got in part B, you get full credit as long as you take your numbers and put them in here. Same thing here. If you made a mistake up here, then these two numbers will be wrong. But if you use the ones that you got and put them in this formula, that's why it says your values, so that I could avoid penalizing you in multiple places for the same mistake. And yes, even if this same sort of question shows up, if you'd written sine of alpha is banana and cosine of beta is grape, and you'd used banana and grape here, I would have given you full credit. The whole point is for you to say, this is the number I got, and now I'm going to use it.
Is that the only situation where like one formula affects the following ones?
Yes, I will. If you have a cascading mistake, you only get penalized for it in the first place. Now, I will say that there are places where a cascading mistake is a larger issue and places where it's a smaller issue. In this case, I think it was a very small issue. As long as you had numbers, you could use them. As long as you used them correctly, you got all the points down. As a matter of fact, a couple of people I simply wrote, error from part A. That's all I wrote. Please?
Do we need that or one?
You will get the two formula sheets that I have used so far, the conic sections one and all of the identities. So you'll get this page and you'll get this page. And then you get an index card, just like you had on exam 2. You can add to it. You could use the same index card. I would recommend that you write a new one, but you can go back and add stuff from chapter 9, stuff from chapter 5, as long as it maintains the same status as before with no worked out examples. And there are a whole bunch of index cards over in the Math Enrichment Center in all sorts of neat neon bright colors, so you can have whatever card you want. You turn it in with the exam, I attach it to the exam, I look it over, make sure there aren't examples on it, then I grade your exam. But you get these attached. More questions?
The section we just did.
The parametric equations.
One was like R equals
Oh, the polar.
any number, but then two trig.
Okay.
Or two trig, cosine and cosecant or sine. How do you, what is the steps for?
Well, it depends on what the question is asking you to do. So, for example, this first problem says here's 5 cosine theta, cosecant theta. Tell me about the symmetry of this problem, right? So, I don't like working in cosecant because there isn't a cosecant on my calculator, but cosecant is 1 over sine. So now I can check symmetry. I can graph this if I want, but I'm not going to. I'm just going to do the checks algebraically. Symmetry with respect to. There were 3 options. Option number 1 was the polar axis. That's the x-axis. And if I swap all of my thetas to minus thetas. I want to know if the equation comes out the same or it comes out different. Now this is where I need even and odd. So if I put a minus sign here, that's the same thing, right? But when I put a minus on the sign, the minus comes out front. Now that minus is going to come all the way out front. That's not the same thing, is it? That's the opposite thing. So that means that I should not expect the graph to automatically be the same on top as it is on the bottom. If I want to check symmetry on the pole, then instead of replacing theta with minus theta, I replace r with minus r. Or I replace theta with theta plus pi, because that would rotate us 180 degrees, right? So if I put a minus r, that's going to look like this, right? Because this is minus the original equation. So I think I want to try the other one. Okay. That's going to make this r equals 5 cosine theta plus pi 1 over sine theta plus pi. And now my brain goes, that's disgusting. I don't like that at all. But cosine over sine. Cosine over sine is another trig function. Cotangent. And now I say to myself, wait, cotangent. Tangent and cotangent have different period than sine and cosine. What's the period of a tangent or a cotangent? Just one? 1 pi, which means this is exactly 1 pi out of step with the original, isn't it? And since the period is 1 pi, these are actually the same. The original equation matches the shifted equation. And that means that everything that happens up here in the first quadrant happens exactly the same down in the third quadrant, only upside down. And everything that happens over here in the second quadrant happens upside down in the fourth quadrant. So if I took the picture and I turned it 180 degrees, I would see the same thing. Last but by no means least, with respect to theta equals pi over 2, the y-axis, right? Now, the problem when I do this is that I'm going to need those identities from my sheet. Because now what I get is I get r equals 5 cotangent pi minus theta. And I don't know what to do with that. But on my formula sheet, I have a formula for doing differences, right? Way back in my trig formula sheet, since cotangent is 1 over tangent, I can swap that out. And everywhere I currently see that cotangent, I can put a tangent. Tangent of subtraction. There's my formula for tangent of subtraction right there. That's ugly, but I can use it. With me so far? I mean, I'm not thrilled by this. What's tangent of pi? You have a calculator. You don't have to do that in your head. Say that again. 0. Tangent of pi is 0. So here, tangent of pi is 0. I get 0 minus tangent theta. Here I get 1 plus 0 times stuff. That's 1 plus 0. That's just a 1. Wait a minute. That's 5, 1 over negative tangent theta. That's negative 5 cotangent theta. Those are not the same as the original equation. I have that extra minus sign, right? If it was the same, I'd be able to say, yes, these should be symmetric. But it's not the same, so they don't have to be. Let's graph. Make sure I change to the right mode, because right now I'm not in polar. Now I am, and I have 5 cosine over sine. 5 cosine theta over sine theta. I'm going to put that on the standard window. Is the left side the same as the right side? Well, kind of. The only one I know is guaranteed is if the symmetry goes this way, right? If I turn this 180 degrees, it'll be the same picture. But it does kind of look like I should be able to fold it top to bottom. Why does it look like that if our first thing said no? Because when we flip it over, technically we're flipping it over both ways. That's what the symmetry that rotates tells me, the symmetry in the pole. Well, because this graph is rigged, I couldn't guarantee it from the equation. But what's happening over here is not the same as what's happening over here. It's the same as what's happening down here. Only they look so freaking close together, don't they? This is annoying to me because the graph gives me one thing, but this doesn't confirm it. So the picture looks like it should have all the symmetry, but the equation only tells me we know symmetry on the origin. So you see the process of swapping out one or more of the pieces and then using the formulas I have to make the equation as simple as I can. Does this look like the thing I started with? The answer is yes, then I have the symmetry. If the answer is no, then I can't guarantee it. Doing symmetry in polar is not common, a piece to exploit further on. We do it in a couple of different places. We use it. Matter of fact, I was using it last week in Calc 3 of all places. So it shows up, but way down the line. More questions? Yes? Talk to me. Sine of theta equals 2 over 7. Okay. The sine is 2/7. That happens in what quadrants? Where is my sine a positive number? Great. Now, sine measures a triangle here, yes? Sine is which two pieces of my triangle? Great. So I can figure out what this angle is. This particular angle is the inverse sine. Right? I don't know what that number is off the top of my head, but it's the inverse sine. So I grab my calculator and I say, what is the inverse sine of 2 over 7? Now, my calculator is in radians, so the first thing I have to do is convert from radians to degrees, multiply by 180, divide by pi. I wanted my answer to the nearest one decimal place, right? So that's 16.6 degrees. But that's only the answer in quadrant 1. Over here, there's a mirror image picture. Right? And the other angle I want, we just got this one. Now I want this one. How do I find that angle? Say again? Why would I multiply by 2? But I want to go all the way from here to there. So you're right that I want to do that, and the reference angle is 16.6, but this other angle is just 180 minus 16.6. I only need to subtract it off once. Which is what? 163.4? There we go. And if I'm only looking in one trip around the circle, then that's it. There's an answer in quadrant 1, there's an answer in quadrant 2, and then I'm done. Now later, in exam 2, I said find all solutions, right? How would I change this if I wanted all the solutions? Yes, but I would add 2 pi's if I was in radians. I'm in degrees, so I add 3/60. So it would be plus n times 360 degrees instead of plus n times 2 pi. The only difference. Which is why we tend to do solving all of them in radians rather than degrees. Better, David? All right, more questions. Yes, sir.
Finding exact values is. So what are the steps to finding exact values?
So,
I'll give you an example.
I can do it here. So, what is the cosine of this angle? Because I don't know what cosine is. I could use my calculator, but I want an exact value, right? So I say to myself, wait a minute. If sine of theta is 2/7, then I have this triangle that we drew up there, opposite over hypotenuse, right? But cosine is adjacent over hypotenuse. So I need to know what's that side. So I'll solve a squared plus 4 equals 49 using Pythagoras. So a squared is 45. That means that a is the square root of 45. Now, I don't care whether you simplify that square root or not. That doesn't matter to me. But now I have the value for adjacent, which means if I want cosine of theta, that's the square root of 45 over 7, adjacent over hypotenuse. You could give me all the rest of them, right? Tangent of theta would be opposite over adjacent. Get some tight. Secant is 1 over cosine, or it's hypotenuse over adjacent. Cosecant is hypotenuse over opposite. And cotangent is adjacent over opposite. So once you've built the triangle, you can figure out all the other trig functions.
So if you're subtracting the cosecant, the sine, first one, the sine of that angle minus the sine of pi over 6.
Oh, okay. So,
Well, no, that's fine too. I forgot that.
So now, well, that's like the question that we were asking about at the beginning with the cascading issue, right? So I'm stuck trying to do this off the fly. Let me do it this way. Pi over 12, right? That's not an angle I know. Yes? That's an angle I don't know off the top of my head. So what I can say is, well, wait a minute. Pi over 12 is half pi over 6. And pi over 6 is an angle I do know, right? So finding this is the same as finding that. And now my brain goes, whoop, 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 half an angle. Half an angle. Now you were saying about adding or subtracting, right? But then my brain would be like, how can I break up the angle into things I know, and then I can use these. So this is, according to my formula right here, the square root of. Now there's a plus or a minus in front of this. No, the formula has a plus or a minus. Sine of alpha over 2 is plus or minus 1 minus cosine alpha over 2. So that's the formula from the formula sheet. And now I say to myself, do I want the plus or do I want the minus? I need to know, where is this angle? That angle's in the first quadrant, which means sine should be positive. And now, tell me, what is the cosine of pi over 6? Square root of 3 over 2. There you go. There's your exact value. And you can leave it just like that.
So find the value of what's being asked.
Right.
And then plug it in as far as some difference.
Right.
Plugging the actual values, and that's the answer.
Yes. I don't remember whether it was sine of alpha plus or sine of alpha minus, but let's assume for the moment it was sine of alpha plus. Remember, in the problem that you're referring to, we had to figure out this number, we had to figure out this number, but we were given those two. Or maybe it was the other way around, but you had to find two of them. These were the ones you were given. These were the ones you found. You found those this way. Then you would plug those values in here. Now, you don't have to use the triangle. You could use another identity. But I think the triangle might be easier. It just takes up more room to draw the pictures.
This is all the assumption that it's all right triangles.
Even if it isn't. Like, say I said that the angle was in quadrant 2, not quadrant 1. well, then I'd know I want to use the right triangle, but then I'd want the other angle. Or if I know the cosine here, what if I tell you that the angle is actually in quadrant 2? Well, then cosine is negative. I'd put a minus sign. Tangent is negative. So I'd be able to adjust these numbers with a plus or a minus depending on which quadrant I'm in. And then I plug those numbers in here. So yes, my base assumption is that I am going to do right triangles wherever I can get away with it. And once I do a right triangle, after that, I'll figure out, do I need to be in a different quadrant? Like I think in one of them I said, hey, the angle's actually in quadrant 2, so the cosine is going to be negative. In this one, I think the angle's in quadrant 3, so the sine is going to be negative. I need to remember where I am, so I know whether I put a plus or a minus on it when I'm done. But I absolutely should use the triangles or the unit circle picture to solve for the values in question. It's still Pythagoras, my favorite Greek geek. More questions? Yes, sir. Verifying an identity. Verifying an identity is a roadmap problem. So we have a starting point, we have an ending point. You have to figure out how to get from point A to point B. That's all we have to do every time is figure out what the right connection is from one to the other. Let's see, that's chapter 7, section 1, I believe. Before we started coming up with all these crazy formulas, yes. So, stuff like this. All I have is a formula. I got to go from the right side to the left side or the left side to the right side. Let me pull one of these out of thin air. 65. I'll write it down. Problem says 1 minus cosine x over sine x plus sine x over 1 minus cosine x should be equal to 2 cosecant x. The book says verify the identity. That means they say this is true. I want to start at one side and get to the other. It should be true. That's disgusting. But I say to myself, the right-hand side is fairly simple, 2 cosecant x. The left side is disgusting. So I'm going to start with the crap on the left. Try and make it nicer and nicer and nicer and do whatever things I can to simplify that and hopefully end up on the right-hand side. So the first question is, hey, on the left-hand side, I'm trying to add 2 fractions. What do I need to have to be able to add fractions? So let's make a common denominator. That means the first fraction, which currently has a denominator of just sine, needs to have the 1 minus cosine x inserted into it. And I have to put it on the bottom and the top because the only thing I'm allowed to multiply by without changing stuff is 1. Plus this fraction has the 1 minus cosine x part, but it doesn't have the sine x part. So we'll put that in. So multiplied by 1, here the 1 looks like this, here the 1 looks like this. And I did that so that I would combine the bottoms. Dan, you're looking at me like I've just slapped you in the face with a fish.
Yeah, I'm trying to figure out how you try to multiply cosine by 1 minus cosine. You won't do it to both.
Well, there's already a 1 minus cosine here. I don't do anything to this side at all. I don't do anything.
Well, about that side.
Oh, you mean here?
Yeah.
Right. I only did that on this fraction because it's already on the bottom of this fraction.
Okay.
So I didn't need to stick it in on the bottom because it was already there. What I needed on the bottom of this fraction was this.
So
What I needed on the bottom of this fraction was this.
So when it falls on that side of the equal sign, each fraction by itself.
Yes, because the next step is to combine them. And when I do that, I have this. I think part of the issue of what you just said to me, Dan, is something that is important in general. You said the other side of the equal sign. I'm making believe that I'm just looking at the left side. And I'm just going to mess with this until it turns into, magically, poof, this shows up. Now that's going to take some work, and I'm not quite sure what direction I should go. So I said, well, let's do the arithmetic. Let's do the algebra necessary to add those fractions. Make a common denominator, combine my garbage. And now, I multiply out. 1 times 1 minus cosine plus cosine squared plus sine squared over 1 minus cosine sine. So far, so good? And now I say to myself, wait, I see a cosine squared and a sine squared. What's that equal to? Which makes this 1 minus 2 cosine x plus another 1 minus cosine x sine x. Yes? But what? So if I combine those, that's 2 minus 2 cosine x, 1 minus cosine x sine x. I'm getting warmer. I'm getting warmer. There's a 2 in both pieces on the top, right? Factor that out. What goes inside that empty set of parentheses there? There's more. Because it's 2 times 1 and 2 times... Wait a minute, that's the same as this, isn't it? And these are being multiplied. So I can cancel that with this. That's over sine. What's 1 over sine x? Cosecant. And what were we aiming for? Da, 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 da. I made it. Please notice, there were two important things here. The first is that I said I need to start with one side and ignore the other one. Only manipulate that one expression. I'm not manipulating both sides at the same time. I'm only going from, in this case, the left side, work, 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 and ended up at the right side. Now you could, depending on the identity, start with the right side and go work, 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 back towards the left. You could start working on the left side and go, I'm stuck. Let me start working on the right side and go, oh, wait a minute. I get to that same place I was stuck before. Now I know the path. In a very realistic sense, you are in charge of how to make the connection from one side to the other. But I think the most direct way, pick the one side that's uglier to you and mess with it. Do the algebra, trig substitutions with our formulas if we need to. Use the identities we already have, like Pythagoras, sine, 1 over sine is cosecant. Use those things to adjust and manipulate until you run into your target other side. Verifying identities on its own is only mildly useful as a skill unto itself. But the ability to take a complicated looking expression and replace it with a much simpler expression, that's incredibly valuable. Because when I have a really complicated expression, it's going to make all my other stuff harder, whatever else I'm doing with it. And we'll see that a lot in Calc 1, in all sorts of other places in math, in discrete math. And that becomes, in a sense, a reducing idea. Take something ugly and complicated, make it simpler, and then do what you need to do. Part of what we do in object-oriented programming, we lob things out to subroutines, right? I don't want to deal with it. You deal with it. Somebody else already wrote this code. I'm going to use that piece. It'll spit back the thing I need, and then I can go from there. Algorithms analysis talks about that sort of efficiency in the CS program, CS 341. We'll see it in lots of different places. Better? All right, hit me again. Of?
D of x equals to 3 sine of 2x plus pi plus 2.
Pi over what?
3
plus 2. Great. So this is a sine curve, and it's been adjusted to hell and back. Now, I think that actually asked not just for sketch the curve, but it said, what's the amplitude, the period, the phase shift, and the range? There are 4 numbers here, and each one changes something different. The amplitude is changed with the vertical stretch. So instead of the normal sine function, which goes from -1 to 1, this one now goes from -3 to 3. But wait, those are y values, right? The y values got bigger. But this adjusts y values also. I moved my y values up by 2. That now tells me the output set, right? The output is the range. So this is my range, which means the y section of my graph is between -1 and 5. The middle of it is at 2, because we go up 3 and down 3. The middle two numbers, that adjusts the period and the phase. Pi over 3. And the formula out of the textbook was those were B and C, those two numbers. So the period becomes 2 pi over the absolute value. The phase shift is minus the number there over that same B. So here my period is 2 pi over 2, which is just pi. And then the phase shift is minus pi over 3, also over 2, giving me minus pi over 6. Now that means we do one full cycle in a length of pi. But this says you need to back it up pi over 6. So each of these marks is a 1/6 of a pi. Took my 1 pi, I divided it up into 6 bits, and I took 1 extra bit on the other side. The reason I took the 1 extra bit is because that's our shift. All right. Normally, the sign goes from the middle, up, down, and then back to the middle. The middle is at a height of 2. We're going to go up, starting here, because we shifted to the left, instead of starting here. We're going to go up and come down. 1, 2, 3, 4, 5, 6. We're going to finish here. Up, down, and back. That means the middle is there. So we go up and down between here and here. Halfway between those two. Up, down. Halfway between these two. Down, up. Now, I should check. I need to get out of polar and back into y equals, so I change my mode back to function. And I put in the equation we were given. The equation we were given is 3 sine 2x plus pi over 3, close parentheses, plus 2. My window. I want to see if I can see this picture. So I'm going to make my window go from minus pi over 6 to 5 pi over 6, from negative 1/6 to 5/6. And I'll make my marks pi over 6, so that way the marks match what I see here. I want my y's to go at least as low as -2 and at least as high as 6. And this should be in the middle of my picture here. The middle is at a height of 2. The highest point is at 5. Between those two marks, the lowest point is at -1. Between those two marks, this is exactly where I line everything. Notice what I needed to remember: vertical stretch, vertical shift, horizontal stretch, horizontal shift. Those two formulas for the horizontal. Multiply to make things bigger up and down. Add or subtract to make things move up and down. Multiply inside to make things squish or stretch left, right. Add or subtract inside to make things shift left or right. A long number of years ago, I taught physics here. And one of the things we did was, there is a port on your graphing calculator that looks like a headphone jack or a USB jack on your calculator. Well, now they're on the side instead of the top for the newer models. You can hook a microphone to this. They actually made a radar device. A little speaker microphone combination that put out sounds and would tell you how far away something was. Turn the calculator to a range finder. But if I just turned on the microphone, I could set my calculator down and say, record this sound. I gave my class a tuning fork where I had covered up the number. And I said, what note is this? I struck the tuning fork, and the calculator listened to it and graphed the sine curve from the vibration of the tuning fork. And what we had to do was figure out what the period was. Because once you knew what the period was, you knew how many times it was vibrating a second. This particular tuning fork was vibrating 256 times a second. That is middle C. This one over here was vibrating at 880 vibrations a second. That's the A above, one octave up from middle C. We took a glass of water and struck the glass and asked what note it was playing. Then we drained half the water and did it again. Drained half the remaining water and did it again. This is how you tune an instrument, people. When you adjust the slides on your trumpet, when you adjust your backslide on your trombone, when you adjust the tightness or interconnection between the neck pieces in the saxophone or in the clarinet, you're adjusting the tuning, you're adjusting the frequency, adjusting your sine curve. Useless. I never do it anywhere. Do you know you can charge $40,000 to tune a pipe organ? Because you have to do this on every single pipe. Pipe organ over in St. Joe's, before it became strictly decorative, was tuned. I kept one of the pipes. They had a set of pipes that they weren't going to put back up. And one of them was adjustable. So I took it to the physics lab and we tuned the pipe by capturing sine waves. Anyhow, Useless, never using it anywhere. More questions? Yes, sir.
Looking at the notes, what is a co-function?
So you have sine and cosine, secant and cosecant, tangent and cotangent. Those are the co-function pairs. So the co-function for sine is cosine, the co-function for cosine is sine.
So it's a inverse?
No, it's a complement. So remember in our right triangles, we have one angle down here, we have another angle up here. And what I know for sure is that those two angles, when added together, give me 90 degrees. They're complementary angles. There's where the co comes from. Because the cosine of this one is the sine of this one. And the sine of this is the cosine of that. The co-function goes with the complement.
Explain why 5 sine negative theta, the same thing as negative 5 sine.
Yes. I'm going to go back here. And I'm just going to look at 5 sine theta. There's the graph of 5 sine x. Yes? If I put a minus sign, that moves this stuff from being positive to being negative. If I flip this graph over, the stuff that's up here is down here. So when I switch from positive x to negative x, I switch from positive y to negative y. So that would be the value over here, right? If I switch over to here, I've got to go from down to up. I've got to go from up to down. So I have to change the y value to turn over. It's based on the symmetry of this picture. The fact that we go diagonally rather than straight across. Now with a cosine, the stuff on the left side of the picture is exactly the same as the stuff on the right side of the picture. So for cosine, these are not opposites, they're the same. And that was the difference between being even and being odd. Oh yeah, all of these are getting scanned and uploaded as soon as I'm done, along with the keys for the 3 homeworks you just turned in and the key to the review sheet. You'll have it all weekend. And then hopefully the sound recording is correct and the YouTube video goes up as well. That usually takes about 15 minutes for the far end to process it, because this is recorded through Canvas and they have to then send me a link to say, hey, we're done processing it, now you can upload it. So that should be up well before noon. More questions? Monday is the last day of classes. I have my normal office hours between 1:45 and 2:45, upstairs at 3:33. Our exam is the next morning. The review session is later this afternoon on Monday. You saw it on Penji. I now give you my official exam advice. There are 3 things you should not do before my exam. You should not stay up all night studying, because you will come in jacked up on caffeine to keep yourself awake for the exam, and your handwriting will look like we're in the middle of an earthquake. Get as good a night of sleep as you can. It's an exam. It's not Damocles' sword hanging over you. No one is in a position where they are failing this course. This is not the end of the world. Third, eat a reasonable breakfast, give yourself time, use the restroom, bring your brains and your calm. It's hard, but I know it's just a math. And in the long run, that's all it is. I hope you have a pleasant weekend. I will see you all on Tuesday. Please, if you have the chance and haven't done it already, please do the evaluation for this course on Evaluation Kit. You should have gotten an email about that. I appreciate it. Thank you.